Hi, for this video we want to talk a little bit about the wheels and brakes. So what you need to know about aircraft wheels and brakes is that they have a lot of similarities with what you might find on a typical car, but they also have some real differences. The big difference on the wheels for aircraft is that they're typically split rim. And what that means is that each of the wheels can come apart in halves, as shown here in this picture. And they're held together with anything from 3 to maybe a dozen or 15 bolts on bigger wheels. The reason for that is we need a really big contact area around the rim between the wheel and the tire, because as we land, the wheel and tire are at a dead stop, and we have to instantly spin them up to a really high speed. And if they don't have a big enough contact surface on the rim, what we call the bead, then the tire will turn on the wheel, and that will rip the valve stem off on a tube tire, and you'll get a flat. The brake disc is bolted typically right to the wheel, as shown here. So this is the actual brake disc that they talk about when they say disc brakes. Taking a closer look at a cross-section of the wheel, some wheels, especially on bigger aircraft, are equipped with what we call a thermal plug. A thermal plug is a little bolt that is made of a metal that is designed to melt at a temperature slightly less than the surrounding structure. And the reason for that is, remember, we attach the brakes to these wheels, and the whole purpose of a brake is to change your kinetic energy into heat. And so if you have too much kinetic energy or dissipate it too quickly with the brakes, the wheels can get so hot that they can cause the tires to explode. And so just before that happens, this thermal plug is supposed to melt and allow all the air to escape out of the tire so that you don't get a big explosion. Yes, you have a flat. It's incredibly inconvenient, very expensive for the airline, but at least you don't have that explosion there underneath the wing, which typically holds a bunch of fuel. Brakes convert kinetic energy into heat. That is their job. The more the aircraft weighs, the more kinetic energy it has. The faster the aircraft is moving, the more kinetic energy it has. The formula for kinetic energy may look vaguely familiar to you. It's kinetic energy equals 1/2 the mass times the velocity squared. You may recognize that from lift and drag formulas. 1/2 rho v squared, where rho is the air density. That's because dynamic pressure in the lift formula is a measure of the kinetic energy of the air. Here we're not measuring kinetic energy of the air, so we don't use density. We use the total mass of the object that we're trying to slow down. So what does that mean for us as pilots? Well, we have to be concerned about the heat in the brakes. We have to turn all of the kinetic energy that we have on landing into heat as we slow down. So what I've done is taken the 172 RG as an example. I used that one as an example because people quite often land this airplane way too fast. In this first example, I've varied the weight. So on the left-hand column, I've given us 2,200 pounds of gross weight, and on the right one, 2,650. So now I do the math. The first thing I do is I turn that weight into mass, and then I just run the numbers. I have to convert 42 knots into feet per second, And what I come out with at the end is 173,914 foot-pounds of energy. And you can convert foot-pounds of kinetic energy into BTU with a simple conversion, and it came out to 223 BTU. So increasing the weight from 2,200 pounds up to 2,650 increased the amount of heat that we're going to produce if we dissipate all our kinetic energy through the use of the brakes. That's a 20% increase in weight, and you get a 20% increase in heat from it. But now let's keep the weight the same, 2,200 pounds in each case, but we're going to increase the speed at which we land. So we're going to let it land a little bit fast. We can see that we get a 20% increase in speed this time, but we get a 43% increase in BTUs. And that's the important thing to remember. If you get in the habit of letting the airplane land fast in an effort to get it on the ground, you have a lot more heat that you're going to have to dissipate. And I disapprove of that both as a pilot, because it's crummy technique to land significantly above the stall speed, and as a mechanic, because I know that that's going to put a lot more wear on the brake pads and could potentially cause a locked brake and a ruined tire and various other problems. Disc brakes are the most common on modern aircraft. It used to be that a lot of aircraft had drum-type brakes. They were really kind of lousy for that application. The disc brakes are much better. They dissipate heat fairly effectively. They're very lightweight compared with a drum brake. They're very easy to inspect and maintain compared to a drum brake. They do not incorporate return springs. Some people consider this a downside on them, because that means they drag a little bit when you release them, but it's pretty insignificant. And it does have the effect of keeping the disc warm so that when the disc gets wet, it dries more quickly. Here's a blow-up drawing of a wheel brake assembly. So this is the wheel here, the wheel halves. And as you assemble the wheel halves, you use the same bolt to bolt the disc onto the wheels. Inside the wheels, there's a set of bearings, one on each side, that are contained, and those are tapered. And the whole thing is held on with a big nut. Here's a picture of brake assembly out of your book. I also have uploaded a set of videos that show you what the brake looks like on a 150 so that you can see how it works. This is a blow-up diagram that's really useful for seeing how the brake caliper is assembled. So this is where the pistons are. When you apply brake pressure on a 150 or 172, you provide pressure to the inside of these cylinders, and they push out on a couple of pistons that push on a backing plate, which has a set of pads attached to it. This is attached to a caliper so that as you push out on this plate, it also pulls the other side, which has another set of pads on it, so that these two sets of pads are squeezing together and clamp down on the disc to slow it down. Here's a picture of a disc assembled in a wheel. This is a little bit different than the Cessna. Notice that it is engaged in the wheel with a set of serrations rather than bolted on. That allows the disc to float back and forth as the brakes are applied. It's just a different way of doing things, but it works the same. Here's a blow-up diagram where we have two discs with a pad on each side, but also a set of pads between them. And that's a way of dissipating that heat over a larger disc surface, so we can dissipate more heat. This is what you have to do when the aircraft starts getting bigger. Notice that we also have more cylinders pressing on it, which means that we increase the force we get for the amount of pressure that we put in the brake line. As aircraft get very large, you may have many sets of rotors and discs in the wheel housing in order to absorb the heat from landing. These can absorb tremendous amounts of heat, but they need time to cool off before you can apply it again. And so some large airliners will have a minimum time that you have to wait between the landing and your next takeoff so that you can be assured that the brakes have cooled enough that they'll be of use to you if you have to abort the takeoff. This is a picture of how the mechanism works in a typical 152, 172, or Cherokee, or any of the others with individually applicable wheel brakes. We have a master brake cylinder under each pedal, and as you rotate the top of the pedal down, it presses on the piston, which is inside the small part, and that provides the pressure that goes out to each individual wheel. Usually only the left side, the pilot side pedals, have the master cylinder under them, and there's a mechanical linkage like this that connect the right side pedals to the left side pedals. So you're still applying the same master cylinders. As aircraft get bigger, you may need to use power hydraulics in order to run them. And it's simply a matter of not being able to supply enough pressure with a simple manual set of master cylinders. So the pedals provide input into the system, and then an anti-skid system keeps the pilot from locking the wheels. This is different than the power brakes that you have on your car. The power brakes that you have on your car are actually assisted brakes. So what the power is doing is helping you press on the pedal. Aircraft power brakes are different. What you're doing with the pedal is opening a valve. And because of your distance from the brakes and because of this power hydraulic system, they don't have a very good feel. They do provide some force feedback so that you can tell what you're doing, but it's really easy to lock up brakes with these. And so we almost always have anti-skid systems attached. We're not going to go over any particular power brake systems, but it's important to know the system for your particular aircraft. Always watch for these hydraulic accumulators. For power brake systems, there's almost always an accumulator to store some pressurized hydraulic fluid in. And all an accumulator does is it's basically a ball or a cylinder with a diaphragm or a piston in the middle. There's compressed air on one side and pressurized hydraulic fluid on the other. The reason that's there is so that if your hydraulic pump fails, you have one or two brake applications left, and you can get the airplane stopped on the runway. If you have a hydraulic failure and use the accumulator, you need to just stop the aircraft and shut it down. You can't guarantee that you're going to have enough applications left to get yourself back to the tie down. Again, these get more and more complex. The important thing is that you know how the system works on your aircraft, and you know the different ways that it can fail and what the procedure is for those fails. This is a picture out of your book that talks about anti-skid systems. Anti-skid systems are usually controllable in terms of turning the system on or off, otherwise known as arming the system. And then you can also select a level of braking. So you can tell it that to brake a maximum, which you would do if you had a shorter runway, or you can have it do anti-skid a little bit more moderately if you have some runway to spare. so that you don't use up the brakes and make the passengers uncomfortable. So when you go to inspect your brakes on a small aircraft like a Cessna or a Piper, check the thickness of the pads. Look at them every day and you'll get used to seeing them. If you're unsure whether it's thick enough, it looks maybe a little bit thinner than you're used to seeing, you can always go grab a mechanic and have them take a quick look. They have the specific standards for it. If you let them go too thin, there's little copper rivets that hold the pads onto the backing plate, and those copper rivets will start gouging into the disc and ruin the disc if you let them get too thin. You want to check for fluid leakage around the brake area. There should be none. And check for brake line damage. Those things do hang out where they can get caught on bushes and things like that. So you want to check the brake lines. And then check for excessive scoring on the disc, but be careful about touching it because they can get quite hot if it was just flown.